Hi there. So this is the second video in our linear homogeneous differential equations of second order pair of videos here. And I just want to pick up where we left off. What we did last time is we looked at a differential equation, and I had you verify that two things were solutions, and from those we pieced them together and made something that was a more general solution, and then we used that to solve the initial value problem. Okay, so let's go through that and look at it in a little bit more detail. Okay, so here's the differential equation that we were looking at. All right, we were looking at this differential equation. The first thing we did is we put it into the standard form that we could deal with, right? So we divided through by x squared, and so we wrote it into the standard form. Okay, and then what I did is I had you verify that these two functions are solutions. And if you didn't do that last video, do it now. Verify that these do indeed solve, well, they solve both of these, so plug it into either one. Verify that they solve these differential equations. And then we had a theorem. We proved the last video that if you ever have two solutions to homogeneous linear differential equation, then any linear combination of those solutions is also a solution. Right? So this is a solution for any constant C1 and C2. All right? And we proved that. And then we used this linear combination to find a solution to the initial value problem, right? Where we specified some initial conditions, and we were able to find C1 and C2 that satisfied these initial conditions. Okay? So the question here is, will this work for any pair of initial conditions? Is this general enough that it will always give us a solution? Or perhaps, do we need another function? Should we have to throw in another function into the works? Maybe I can come up with initial conditions where these won't cut it. These won't be good enough. So the point of today's video is to answer these questions. Okay? So the first thing we're going to talk about is what a fundamental set of solutions is. Okay, so a pair of solutions is a fundamental set or a basis on an interval AB if every solution on AB is a linear combination of those functions. Okay, so that would be saying that, to say that these are a fundamental set, x squared and x to the negative 2, would give us a positive answer to our question that yes, every solution can be written in this form, right? Because that's what it means to be a fundamental set. Every solution could be written as a linear combination of these two functions. So that would mean that every solution could actually be written like this, and so this would be the most general solution. But we need to verify that these are a fundamental set. Okay? So how do you verify that a pair of solutions is actually a fundamental set? Oh, and by the way, by linear combination, I was pointing out that that's just one of these, right? A constant times one solution plus a constant times the other. So how do you verify that a pair of solutions is a fundamental set? Well, for that, we need another term. We need the idea of linear independence. So here we go. A pair of functions are linearly independent on an interval if neither is a constant multiple of the other on that interval. Okay, so two functions are linearly independent if neither is a constant multiple of the other. Turns out linear independence will tell us whether we have a fundamental set, which will tell us if our solution is general enough to constitute all solutions. So let's do an example where we look at we investigate whether a couple of functions are linearly independent, okay? So here we go. Verify whether or not these functions are linearly independent. And I have two sets, okay? So let's look at this set here, x squared and x to the minus 2. Are these linearly independent? Well, what was the definition of linear independence? It says that neither is a constant multiple of the other. Okay, so that means that if I take the ratio of these two functions and I get a constant, that means that they're not linearly independent, right? Because that would mean that one is a constant multiple of the other one. So let's take a ratio. Let's take x squared and divide by x to the minus 2. Let's see what we get. We get x to the 4th. Is that a constant? Nope. Not a constant on this interval. It's not a constant well, it's only a constant for a particular value of x, but not in any interval is it a constant. So yes, they are linearly independent. This is linearly independent. So good. What about these two? Are these linearly independent on this interval? Well, do the same thing. Take the ratio. Is that a constant? Well, it doesn't look like one, but let's simplify it, okay? So let's factor the bottom. So I'll factor out a 5. Let's keep factoring some more. Let's see, this thing factors as, oh, it factors as x minus 1 squared. Look at this. These cancel. That is a constant. That's 1/5. So these are linearly independent. These are not linearly independent. Not linearly independent. One is a constant multiple of the other one. Okay? So that's a check for linear independence. So, so what? Okay? Well, all of this comes together in the following theorem. Okay? It's a very important theorem from your book. Okay? So suppose we have the differential equation of the type that we've been dealing with, right? With continuous functions on an interval. Then a set of solutions on that interval is a fundamental set if and only if that pair is linearly independent on that interval. So remember what this is saying. A fundamental set of solutions is a pair of solutions from which we can construct the most general solution. So that's great. That's what we're looking for to solve a differential equation. We're looking for the fundamental set because that means we can put those together in a linear combination and solve any initial value problem. So that's what we were looking for. And it's saying that it'll be a fundamental set if they are linearly independent. So by checking linear independence, we're verifying that they will be a fundamental set, and so that we will be able to find the most general solution. So this is an amazingly powerful theorem. Okay? So let's put this theorem to work. Let's do a problem. Find the general solution. Find the general solution to this differential equation on this interval, given that e to the x and e to the minus x are solutions. So you're given two solutions. Find the general solution. Well, first of all, let's see if these constitute a fundamental set. Okay, to see that the theorem says is we just need to check to see if they're linearly independent. Okay, so let's check for linear independence. So are they linearly independent? Having trouble writing. Linearly independent, that's what that's supposed to say. So what I'll do is I'll look at the ratio. E to the x over e to the minus x is e to the 2x. Is that a constant on this interval? No, it's not a constant. So therefore, they are linearly independent. They are linearly independent. Great. Now what does the theorem say? The theorem says if they're linearly independent, then they form a fundamental set. Okay? So therefore, sorry, I'm bumping into things on my desk. So therefore, e to the x, comma, e to the minus x is a fundamental set. All right, so what? Well, that means that every solution can be written as a linear combination of these. That's the definition of fundamental set. So therefore, the most general solution is just y equals c1 e to the x plus c2 e to the minus x. That is the most general solution. So we've solved the problem. So just by finding two solutions, verifying that they're independent, gives us the most general solution. Okay? So that general solution will solve any initial value problem for this differential equation. In particular, okay, so next what we're going to do is we're going to solve the initial value problem. It's the same differential equation we had before, but we have initial value conditions. Well, how do you start solving an initial value problem? You find the general solution. So we just said the general solution was c1 e to the x plus c2 e to the minus x. And we knew that because these were a fundamental set. And we know that therefore any linear combination of them makes the general solution. Now, how do I get the particular solution that satisfies these conditions? Well, I need to check y and y prime, so let's compute y prime. And now we're going to check these values, right? So when I plug in 0 for x, I should get 1 for y. So that top equation becomes this. So these guys become these guys. The bottom equation says that when I plug in 0 for x and y prime, I get -1 for y prime. Okay, so here's a system to solve. So go ahead and solve this system, and let's see what we get. So I'll give you a minute to solve it. Okay, so pause the video, solve it. And what do you get? You get C1 equals 0, C2 equals 1, right? Okay, so now we can take our general solution and write down a particular solution that solves those initial value conditions. So plugging in 0 for C1 and 1 for C2 tells us that the solution to the initial value problem is e to the negative x. Right? Okay, so that's it. So some important concepts here. We had the concept of, what did we start with? We had that a linear combination of two solutions is a solution. We had the idea of a fundamental set, right? This is something that every solution can be written as a linear combination of. And then we had the idea of linear independence. So if you can take two solutions and verify that they're linearly independent, then you know that they form a fundamental set, which means you can use them to write down any solution, right? And then we can use that any solution to solve the initial value problem. Okay, so that's it. I'll see you in the next video.